this time we're going to do something a little different. Remember, we do have forces associated with springs. So we're going to take a block and we're going to drop it onto a pan that's on top of a spring. And so we're going to start with a 30 kilogram block. We're going to drop it onto a 10 kilogram pan. So we're not going to be able to disregard the mass of the pan. And it's on top of a spring with a spring constant of 20 kilonewtons per meter. So it's a pretty stout spring. So we're going to assume a perfectly plastic collision, but we want to determine the maximum deflection of the pan. So we've got a couple of things that we have to worry about. One is the original length of our spring is going to be dependent upon that spring without the pan, because the pan is actually going to provide some compression of the spring. We also are going to have potential energy of our block because we're going to drop our block from a 2-meter height. And so we can calculate the weight of our block and have that information before. So in our situation before, we're going to get a little bit of compression of the spring due to the pan, then we're going to drop the block on it. Now, at the point of the collision, we're going to have kinetic energy, which of course our book uses as T, and we're going to drop that in, and that's related to our potential energy. So just using our conservation of energy, we know that the kinetic energy that we're going to put into the system is 588.6 joules, and we can determine the velocity because remember this is a momentum problem, so that we're going to need that velocity, and it's going to come in with a velocity of 6.26 meters per second downward. Now after the collision, we're going to get the block plus the pan is going to give us our compression of our spring. So now let's kind of look at this in its step-by-step step-by-step procedure. So let's just use the conservation of momentum at the moment of the collision. So we've got our mass of our block, we've got a mass of our pan, we've got the velocity of our pan at the beginning. Now remember here, the velocity of the pan at the beginning of everything was equal to 0, but the velocity of the block is coming from our kinetic energy. So we get our momentum after it's a perfectly plastic collision or perfectly inelastic collision, and our masses are combined. And so we can rearrange and solve for our new velocity, which is going to be negative 4.7 meters per second. And of course, that's going downward. That's what that negative sign is telling us. So now we got to look at after the collision. We're going to have conservation of energy. We got a new conservation of energy problem, but now we have a new kinetic energy portion. Okay, we've got a new kinetic energy, but remember we have a perfectly inelastic collision, so kinetic energy, we don't have conservation of kinetic energy, but we do have conservation of energy. So we know the kinetic energy after our collisions related to the velocity going downward. We also have potential energy associated with the spring, and this is going to relate to how we're going to ultimately get our deflection. But let's think about this a little bit before we get to that point, because we said we had to consider the deflection of the spring due to the pan. So we need to know that initial displacement due to the pan, so we can use our work equation to help us out with that, and we can solve for that initial displacement related to the pan on the spring. Now we want to look at the whole system. So the potential energy of our spring when it hits its maximum deflection is going to equal to the change in the potential energy due to the weight of the pan plus the potential energy of the spring due to the deflection, the new deflection. So let's look at that for a second. So here's my spring at my original height. We get a displacement due to the pan, and we get a displacement due to the drop of the block, that's the collision. So we end up with a height h. So let's kind of look at that for a second, because our height h is going to be important because our total displacement of the pan is going to be h plus x. So when we're rewriting that conservation of energy equation, we got our potential energy of the spring is equal to the weight of the blocks combined times that change in height plus our total deflection. So if we rewrite this, I've got the V which is going to equal this right here. But let's look at it a little differently. Let's look at the total energy at the top is equal or plus the potential energy with just the pan is going to equal the kinetic energy at the bottom plus the potential energy at H, that separation at H. Now the potential with just the pan is going to equal that initial deflection that we had, right? It's going to equal that initial deflection with that we had. And we've got our energy that's there. And so we'll end up doing this calculation that shows, and we're solving for our xt, but we have our height right here, and we can show that the total this deflection is equal to 0.23 meters, and the height is equal to 0.225 meters.